So in this video, we're going to see a corollary and an application of the geometric form of the Hahn-Banach theorem. Now the corollary is about strict separation. Now I have my two convex non-empty sets. I know that if one of them is open, I can separate them. I start with two sets that do not intersect. What the corollary about strict separation tells us is if I put some extra assumption on my convex non-empty set, namely I assume that they are closed, and instead of assuming that B is open, I'm going to assume that it's more than closed, it's compact, then I'm going to get strict separation, right? So there's a strict separation of, let's say, compact convex non-empty set, but only one of them needs to be compact. So let's see how that follows from the separation of two convex set, one of them being open, that we've seen before. So I'm going to introduce this difference of the two sets as we've done before, and we're going to do a separation. You remember we did a separation of that set from 0 in our proof of the geometric form of Hahn-Banach. This time we're going to separate this set not just from 0 but from a ball around 0, which will be our open set, and the fact that we have a whole ball is going to give us a little bit of space, and that's going to lead to the strictness of the separation. So the first thing I need to see is that y is closed. So y is wide closed. Okay, so claim y is closed. Let's show that. So let's take un, a sequence in E, and let's take Vn, a sequence in B. Let's just form the difference of these two sequences and assume that it converges. So I'm also going to take a y in X such that un minus Vn converges to y. And what I need to prove, right, prove that capital Y is closed, I need to prove that little y is in A minus B. Now B is compact, so I can extract a converging subsequence from Vn. So there exists Vnk, a subsequence of Vn, such that Vnk converges to something. So there exists Vnk, that's in B to the n, and B is compact, so there will also exist a V in B, such that this V and K tends to V as K goes to infinity. But un minus Vn goes to y, so unk minus Vnk has to go to y, and Vnk converge to V, so unk has to converge to y plus V as k goes to infinity. Okay, but that means unk has a limit, which is y plus V. Vnk has a limit, which is V. So let's call that limit u. That has to be an element of A because A is closed, and therefore I can write y as u minus v, for of course u equals y plus v, and u is in A and v is in B, so this is in A minus B. Alright, so that finishes the proof of the claim that capital Y is closed. Now 0 does not belong to Y. Same trick as before, that's because A intersected B is empty, so there cannot be any, 0 cannot be in the difference of A and B. And the complement is open, right? Because we've just proven that y is closed. And that is critical here because that gives us an entire ball centered at 0, which is not in y, and that stays not in y. So there's an entire ball that does not intersect y. And now I can use Hahn-Banach in its geometric form to separate this ball from the set y. Separated. Oh, I should have reminded you that y is going to be convex as a difference of two convex set. Okay, so yeah, and it's not empty because it contains, well, because A and B are not empty. Okay, so I have this separation, and what does that tell me? That tells me that there exists some alpha and R, and there exists a functional X star and capital X star, such that the corresponding hyperplane separates the two things. So X star of, let's write it this way, delta omega is greater than alpha for every omega in the unit, in the open unit ball. Right, so just scaling by delta to get the ball of radius delta. And in the meantime, X star of u minus v has to be smaller than alpha for all u in A and for all v in B. So that's the separation. Okay, now that I have that, this gives what? This gives that X star of u minus v, that's for all u in A and for all v in B, has to be smaller than X star of delta omega for all omega in B 0, 1. So in particular, I could ensure that this is negative because I pick an omega, and if it turns out to be non-negative, then I pick minus omega, which is also in the ball, and I can take a supremum of this over all elements of the ball. So, and this, by the way, is equal to delta X star omega. So taking the supremum over omega whenever this is negative, I would get that this has to be smaller than minus delta times the norm of X star. Right, now I'm gonna define my epsilon. Okay, it's not a peak, it's a let. Let epsilon be this quantity delta X star divided by 2. Now I have that for all u in A and for all v in B, X star of u minus v is smaller than minus 2 epsilon. Now what does that give me? I'll just put things together now, and that gives me that for all u in A and for all v in B, X star of u minus epsilon is smaller than X star of u plus epsilon is smaller than X star of v minus epsilon. I'm putting an epsilon on both sides. And now I can take the supremum over all u in A on the left hand side, and it would have to remain smaller than the infimum over all v in B on the right hand side. Okay, and now I'm picking an alpha that is between this supremum, that's a trick we've used several times by now, and this infimum. Right, it has to exist. Maybe there's only one point, in which case I pick that point, that value of alpha. If there is an entire interval, I just choose one. And what do I have? Well, I have that X star of u is, so this, because alpha is above the supremum, so X star of u plus epsilon is smaller than alpha for every u in A. And in the meantime, X star of v minus epsilon is greater than alpha for all v in B. And that is exactly ensuring strict separation, which concludes the proof of this corollary. So to finish this chapter, we are now going to see a theorem that extends a very practical tool from Hilbert space theory to general Banach spaces, applying the geometric form of the Hahn-Banach theorem. So this is theorem 5.7 here, and this gives us some form of orthogonal subspaces in Banach spaces. Now, we don't have a notion of orthogonality, we don't have an inner product, but what we do have is a duality product. So given a subspace of my Banach space X, I'm going to define a subspace Y. I'm going to define Y perp to be the set of elements in X star such that the duality product of x star with any element of y is 0. Right? So notice that if x were to be a Hilbert space, I could identify x star with x itself, and then this y perp will be the actual orthogonal complement of y in the Hilbert space. Now, it's not defined as a subspace of x at all, it's just defined as a subspace of x star of all those functional that vanish when testing against element of the subspace of y. You can tell that this is likely, for practical purposes, to play the same role as the orthogonal complement of a closed subspace in a Hilbert space, but the difference now is that it's an element of x star. Now, I'm also going to define y perp as a subspace of x, and that's going to be those elements of x that are annihilated by functionals in y perp. Now notice, let's make a few remarks here. If I were to be in a Hilbert space, in x Hilbert, or if x is Hilbert, then what would I have? I would be able to split x as y bar plus y bar perp, and I would have y perp equal y bar. Right, now here it's very different because you need to remark that y perp is definitely not the same thing in general as y perp and then take the perp of that. Because if I take y perp, I get in x star, and I take the perp of that, I get in x double star, right? The dual of the dual. But the dual of the dual is not the space itself in general Banach spaces. Only in Hilbert spaces do I have all of these identifications. We'll talk about later in the course about reflexive spaces, which are those Banach spaces for which at least you can identify x double star with x itself. So you only have to deal with a pair of spaces, x and x star, and not a whole family of spaces, x star, x double star, x triple star, and so on and so forth, as you would in principle have to deal with in general Banach spaces. So, okay, now armed with these two definitions, we're still going to get a very neat corollary, which is the analog of the typical application of the orthogonal decomposition of into a closed space and its orthogonal complement of a Hilbert space in general Banach spaces. So that's what theorem 5.7 tells us. It tells us that this fact that you can identify y perp with y bar remain correct in every Banach spaces thanks to Hahn-Banach. And this is handy because in particular this tells us that y bar is going to be all of x whenever y perp is all of x. And there certainly is one case where it's obvious that y perp is all of x. That's when y perp itself is trivial, right? If y perp itself is trivial, in the definition of y perp, you're only testing on 0, and any x, duality product with 0 gives you 0. So this is a way to test for the density of certain subspaces. Very often in applications of functional analysis to partial differential equation, in particular, just think of something like Fourier series in L2, for instance. You want to know that certain spaces are dense, right? You want to know that certain decomposition in a certain approximation by finite sums, if you take the limit and take infinite sums, can describe any element of the space. That's the example of when you want to show that every element of L2 can be decomposed as a Fourier series, for instance. So this gives you a very helpful practical criterion to test density of a space. You had it in Hilbert spaces as a consequence of the orthogonal decomposition of closed subspaces, and what Hahn-Banach theorem gives us now is an extension of that into Banach spaces. Testing that y perp is trivial is enough to ensure density. Now let's see the proof of the theorem. We have two inclusions to prove. In the first step, we need to prove that y bar is included in y perp, and then we'll have to prove the other inclusion. Now that's the easiest, I should say, of the two. You take an element y in y bar, you pick a sequence in y that approximates it, Okay. And then what can you say about whether or not y is in y perp? Well, what you can say is that if you take a y star in y perp, y star acting on yn is going to be 0 for all n, right? And that's because yn is in y, and that's literally what the definition of y star being in y perp means. So what we have by taking the limit is that y star y, which is the limit of the y star n, because y star is a continuous linear functional and yn tends to yn norm, has to be 0. And that exactly says that y belongs to y perp, right? Y star applied to y is 0 for every y star in y perp. So that's step 1. That gives us one inclusion. Step 2, let's have a look at the other inclusion. So I want to do a reasoning by contradiction. So I'm going to assume by contradiction, I'm going to assume that there exists an element in y perp that is not in y bar. Right, so what would that give me? Then it would give me that I can separate then y bar and the single point y naught are strictly separated. That's by the corollary that we've just seen, right? A single point is certainly a compact set. Y bar is a closed set. They are both convex. A single point certainly is. And a closed subspace certainly is. And they're non-empty. So I can strictly separate them. Now, what does that mean? That means that I can find a hyperplane. So there exists an alpha. And there exists a, let's call it y star in x star. That is such that y star y is smaller than, there exists an epsilon, I suppose. Let's write it like that, such that this is smaller than alpha minus epsilon, and y star y is greater than alpha plus epsilon. That's what strict separation gives us. Now, okay, I want to remark that y star, that's for all y in y perp, in y bar, and that's for every y, well, in the single point y naught, so that's literally for y naught. Now I want to remark that y star y has to be 0 for all y in y bar. That's because y bar is a subspace. So let's see why that is. I mean, you cannot have an inequality like this, some bound on y star y for all y in a subspace, because you can have vectors of arbitrarily large norm in a subspace. That's the idea. So how can we see that? Well, since for y in y bar such that y star y is some number, and let's say this number is positive, you cannot have everything in every duality product y star y being negative, because if you have a negative 1, you can replace y by -1 and then you get a positive 1. So let's just assume there is a y such that this is not 0. Then you can find a y, either the one you just found or minus the one you just found, such that this duality product is something strictly positive. Now, once you've found that, all you have to do is take y star comma y divided by beta to make this 1, and then let's multiply it by 2 absolute value of alpha, let's say. If you do that, you're going to get something exactly equal to 2 absolute value of alpha, but in the meantime it has to be smaller or equal to alpha, in fact even alpha minus epsilon, and that's a contradiction. All right, so whenever you have a separation like that of a subspace, the alpha for which it happens has to be 0. Right? This can only happen if all the y star y are 0, which is what we've just proven here. So now you put that together with the condition on y star y naught, and what does that give you? That gives you that y star y naught is greater or equal to alpha plus epsilon, which is certainly greater than y star y, which is equal to 0 for all y in y bar. So in fact, this is importantly, this is strictly greater than 0 because alpha itself is greater than this, and then I'm adding epsilon. So I have y star y naught strictly positive, and then I have y star y equal to 0 for y in y bar. So this is telling me that y is in that y star is in y bar perp, which is even bigger than y perp. So I have y star in y perp, yet y star y naught is strictly positive. So if y star y naught is strictly positive, and y star is in y perp, then y naught cannot be in y perp, because if it were in y perp, then this duality product should be 0, and it's not. So y naught is not in y perp, but I took it in y perp to start with. So this gives me my contradiction, and this concludes the proof. So we've just proven both inclusion here and there. So we've proven that the closure of y is always y perp. That's true for any subspace in any Banach space as a consequence of the geometric form of Hahn-Banach theorem. And that allows us to conclude that a subspace y is dense just from the fact that its perp as a subspace of x star is trivial. Okay, and that concludes chapter 5.